Uh, Here we go. Go ahead, please.
Hello, everyone, and thank you very much for the introduction and for the invitation to the MIM webinar. My name is Jihoon Park from Seoul National University, Korea, and I'm here with you to present my work last year in date 25, Compass, a compiler framework for resource-constrained in-memory computing accelerator. Currently, I'm working on a compiler framework for my own self IMC SoC project that I taped out last year as well. Without further ado, I'll go on with my paper. So let me introduce you about the deep learning compilation landscape for IMC hardware first. So as you all know, deep learning models are rapidly increasing in sizes, and in-memory computing is also an emerging as a promising solution for accelerating computation. And there's a lot of deep learning compilers out there that targets a lot of hardware diversity. So as you think of CPUs, GPUs, NPUs, they are all diverse hardwares that want to accelerate deep learning models. But there is also a need for optimizing for IMC. So there's some need for IMC-aware compiler optimization techniques. The reason is clear. The target hardware that in-memory computing uses is that there is a fixed size crossbar array inside the deep learning accelerators that can be of various rows and column sizes. There can be various devices, and there can be various number of counts inside the deep learning accelerator. So it makes the hardware of the IMC accelerator very diverse. So in that way, there should be some compiler techniques that optimizes for IMCs. But there are some challenges of adopting the traditional compiling method on an IMC chip, because there's an inherent difference from the GPU and NPU architecture from an IMC architecture. The main thing is that the IMC architecture performs a computation where the data is stored, and they want to minimize the data movement as much as possible. So they usually take the weight stationary approach so that they don't move the weights as much as possible. And also the data transfer, even the activation and the intermediate data is performed at the crossbar level of granularity, because the weights are separated into these fixed size IMC arrays. And also they have higher write cost for the weights, so that also have to be accounted. On the other hand, GPU and NPU relies on fast data transfer between the cores and local buffers, and the sizes of the cores are different when it's integrated in the IMC-based methods. And these data transfers are also done with smaller data granularity than the crossbar level of granularity. So some of the compiler for IMC architecture requires to manage high memory write cost, and they have to efficiently partition and schedule with these level of granularity and within the IMC's limited resources. There are some previous studies on IMC-aware compiler. One is PIMComp from DAC 23, and one is Puma, ASPOS 2019. These two papers were my baselines and what I've usually referred in my paper. They both share a similar chip architecture. They have a hierarchical structure to maximize parallelism at each level and minimize the communication cost. Let's see at PIMComp, they have the three-level structure with the chip and the core and the crossbar array from the largest to the smallest hierarchy. So you can see that there is an array of crossbar inside the core, and a lot of cores are put together, forming a bus or a chip network as a chip. Similar goes with Puma. They have another hierarchy called tile, but they all share the same architecture. The architecture of the IMC frameworks are kind of going to the same way, but the compiler has some limitations. These two papers target to put all of the weights on the chip. Well, that's a nice thing to do because having the weights on chip makes it efficient, but that's not all. That's not the thing that works for all compilers. So what about the large models that cannot fit on a single resource constrained IMC chip? So these models should be partitioned with the support of compiler to fit on the chip. So that weights are partitioned and assigned to these fixed and small size crossbar arrays that are numerously in the chip. So this model partitioning is the key word that we have to take, and we have to do this in order to execute the large models. So here's my hardware architecture overview. So we take the same similar hierarchy structure, and we have this chip that's pre-configured, and we want to make it execute the model in multiple partitions. So we do a weight replacement for DNNs that exceed the memory capacity of a single chip. So when the DNN have DNN weight footprint is much longer than what a single chip has, it partitions the model into a subgraph that can be put on each chip, and it can be executed in a serial manner at each time frame. During this weight replacement scheme, we have to follow these two things. The IMC core retrains the weights until the computations are complete. And then the core loads the weight from the DRAM and write that new weights to the PIM core. And during the stage, you can see that you have to also store the output of the intermediate data to the global memory. And then after replacing all the weights, you can load the input from the global memory to the core to execute, and you can do that over and over again to execute multiple partitions. This is very similar to what NPU does. When you think of an NPU or maybe a GPU, you usually think a layer by layer execution where you put the weights or you stream in the data to calculate from the global memory to the P's. And then after you calculate a layer in a tiled memory, you store the output. And then you do that for another layer and another layer. That seems really similar to this executed partition scheme. But one thing that is really different from NPUs is that the previous and most PIM compilers focus on executing multiple layers, mapping multiple layers to the PIM core at once, and executing multiple layers and storing the output of the last layer of the mapped ones in this stage. So the main thing that we have to do is how to get this partition, how to efficiently partition that we can map it to have the optimal performance. These are the 3 steps we go through and to find the best partitioning scheme. First of all, we generate a number of partition groups. By partition group, we mean a model is partitioned into n partitions, and a partition group consists of a number of partitions that form a whole model. So you get a hardware configuration and the model configuration, and you decompose the model into small units called partition units. these units all are the smallest unit that can be fit on a crossbar. And then we want to reassemble these partition units to create partitions that can be fit on a single chip for each partitions. And we call the whole partition units that form the partitions as a partition group. We generate a number of partition groups randomly, and then we want to find the optimal partition group by modifying it through a genetic algorithm. The process goes like this. So we take one partition group, and we have an on-chip optimizer that utilizes the previous works to do the core mapping and weight replications. So when you think of the PIMComp and the Puma compiler, they are already compilers that map compilers that works when you map the weights wholly on chip. So when you get a single partition, this maps onto the chip wholly. So you can get this partition, put it into on-chip optimizer like Puma or PIMComp. You can do the core mapping and replication that optimizes this partition for that chip. So yes, so the weight replication can accelerate the latency for that chip and fill up the remaining areas of the chip for this partition. And P1 can be done the same for another time step, and P2 can be done for the next one. So the existing compilers can be used to optimize each of the partition on the chip, and we can also calculate the fitness, which is the estimated latency or energy efficiency of each partition. Then we gather up the fitness and calculate the latency or performance for the whole partition group, which models the model latency or model power energy efficiency. And then for this partition group, we might get the PG0, and for another we can get PG1, and there can be a lot of fitness calculated for a random partition groups. And from in those partition group, we select the ones to mutate. We can this will be dealt later in deeply, but we can think of that we can select the top K and then we mutate over them using merge, split, and move and fixed random that moves around the partitions between the partition units between the partitions. So you can think of moving you can think of like moving a subnode of a subgraph into another graph in this merge, and you can split a subgraph into two different subgraphs and split and so on. So you go on through this loop of mutating the partition group to get a better and better fitness, and then you get the latest top one of the solution, and you generate the instruction from that. Then you can get the real result of the compiler. So to go deeply onto before diving deeply onto the compiler techniques, we show you the hardware abstraction we take. This is really similar to what PIMComp, the previous work, has done. We actually extend from that work from the open source repo, and we extend their ISA to support weight loading from DRAM and weight writes to the IMC crossbar arrays. We have the same 3-level structure, and we have the instruction set architecture for each NVMe unit, vector process units, and the core that loads the memory and stuff. Then we have this hardware, and we parameterize the number of cores and crossbars that we use to limit the chip sizes. And we have this global local memory specification summarized in this table. So in this resource constrained chip, we have to put the model. And according to the overview that I've explained above, I use partition units to partition the model. So the partition unit is the smallest unit for model mapping, and they can be thought of as we transform the original model into smaller nodes that can be fit into a crossbar like this, and then we consider each node partition unit. A partition is a set of consecutive partition units where we can say that 4 of these partition units consist of a partition, and this node is starting point, and then there's another 6 partition units forming the next partition. So each partition fits into a chip, and executing one partition after another requires global memory communication, because you have to store the output data from this and load the data here. And also you have to replace the weights for the next partition as well. So the partition units, we divide the model into partition units, and we want to find which partition to put on a single chip. So we do that by using a submodel verification. We first put a random threshold that divides the models into segments, and then we have a verification if it fits onto a single chip. So this is the formula to do that. But we actually pre-compute the ranges so that we can avoid redundant calculations. So for each model, when you have a starting index of a partition unit, you get how many partition units can be valid for a single chip, and you can pre-calculate it into a table like this. For small models, it can just fit them all, so the table looks like this. For larger models, the layers themselves are very large, and there's a lot of number of blocks in, so that a smaller the model cannot fit in one chip. But we have to partition it using this scheme. Then we design a partition group fitness, which is the sum of a partition fitness. So for each partition, we can set for each partition we have the number subgraph X, and we have a determined set of weights, a subset of weights, but we didn't really map that onto the chip yet. So the GX is the weight mapping state. So given a weight set, a sub weight of X, we do the weight duplication and core mapping, which gets the weight state, weight mapping of Z. And then we go on and estimate this mapping's performance using a simplified instructions, which gets the on-chip end-to-end latency. So this is the fitness that you want to use to minimize in the genetic algorithm. And when we estimate this end-to-end latency using simplified instructions, we follow the implementation of previous work, but we include the wait load and writes by extending the ISA. This is a little bit of detail, but we first go on and find if the previous works simplify instructions really estimate the latency well, but we found that there's some mismatch between the real latency and the estimated latency in the existing implementation. So we made some adjustments to the fitness function and reduced the mismatch by reflecting the vector operations and inter-core communication into the PIMCOM's implementation. So this is just a little fix to make it better, make it work better on a partitioned scheme execution. Now that we have the fitness of each partition, we go through the genetic algorithm pipeline so that we can do the random generation, then the selection and the mutation. So for 100 generation, we do the partition optimizing, and we do a cutoff when the generation doesn't really go on perform better and better. So we get a candidate from the random generation, and then after one generation after another, we see that their fitness, the latency gets lower and lower. And we can see that their number of partitions kind of reduces that, kind of gets from 6 to 8 to 9 to 10. So that we can find that this is the best number of partition at the end. So for the selection, this is the most important part of the optimizing. We have a lot of partitions inside the partition groups, and this optimizing between the partition is a delicate task because there's no directive for it, and if you change one partition from another, you have to calculate the whole thing. So this is really hard. There's a lot of calculation going on through this. So we have to find out which partition is most appropriate to be mutated, because there are so many partitions and so many ways to form a partition. We cannot calculate everything. So we cannot do just sweep to search for it. So the answer to this question, to find which partition is most appropriate to be mutated, is that you want to change the location of a partition, and then you can get the improvement rate for that span of partition units. And you also track the expected improvement for each partition unit span. And if it's better than that, you want to go to that mutation method. And if this is below the expected method, expected growth rates, you don't want to take that method. So we use the 4 mutation methods: merge, split, move, and fixed random. And we try to find out the fitness. We try to find if its fitness will improve or not for that span of partition units. So using that method, we go through the genetic algorithm and make the optimal partition group. We get the 2 baselines to compare in the experimental result. Since there was no compiler framework for splitting up and executing in multiple partitions, we have some very basic baselines. The first one is greedy split, where we allocate as many layers as possible into a single partition. So that allows the memory capacity inside a single chip. So just sequentially, we try to put in the weights into that IMC chip, so that partition 0 consists of convolution 0 to 4. Partition 1 can consist of the later convolutions, and convolution 5 cannot fit onto this partition because there's no weight, no space left in the IMC cells. The baseline 2 is layer-wise splitting, which is very similar to what I call layer-by-layer execution in the MPUs. So we include a single layer in each partition, and we do the weight replication to accelerate each of the stage as much as possible. So here is our main results. We do the experiment for 3 different network types, and we evaluate for different batch sizes as well, because when you execute in a partitioned manner, we have to change the weights every partition. And then if you only execute for one batch, the weights are not really reused that much. But if you increase the batch sizes, you can reuse the weights a bit more. But the greedy layer-wise compass all has to partition the model in a small chip sizes. So, and in larger chip sizes, they can fit in. They might fit in for the greedy method. So, going back, and this is 3 different models and 3 different chip sizes and the batch sizes, and we check we measure the throughput of each method, and we get an average of 1.78 higher throughput, and we can see that increasing the batch sizes improves the throughput as well. For the energy and energy delay product, we get this graph where the greedy method has the lowest energy consumption. This is because the greedy method puts in as much as weights onto a single chip as possible, so that weight loading is minimized. But we perform better than layer-wise because we have smaller partitions than the layer-wise method. And in optimizing both power and latency, we calculate the energy delay product. Because we have a better throughput than any of these methods, considering both energy and delay, we get a better performance than the greedy and the layer-wise methods. So compared to greedy split, we have the 1.28x improvement, and compared to layer-wise split, we have 2.08 improvement in EDP. So to conclude my work, we made a novel framework that enables the execution of larger models on the same IMC hardware. We consider the weight and data movement between the partitions by extending the ISAs and implementing the compiler that estimates the latency. And we automatically partition the model to balance the layer-wise pipelining and reduce the off-chip memory access through the genetic algorithm. And we achieve higher throughput and better EDP than the baseline partitioning methods, and show that effective partitioning and replicating layers boost the performance. Yeah. Thank you for listening to my talk, and I'm very free to answer any of the questions.
All right, thank you very much, Jihoon. Let me pause the recording.
Subscribe the channel to get the instant updates on our webinars.